Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover trigonometry. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with angles and how we measure them. Degrees, minutes, and seconds. The degree is the unit of angle measure inherited from Babylonian astronomy, the same base 60 counting system we traced in the previous section. One full counterclockwise revolution about a point equals 360 degrees. A right angle is 90 degrees, a straight angle is 180 degrees, and the three interior angles of any triangle sum to 180 degrees. Figure 6. 4 fundamental angles. A full revolution of 360 degrees, a straight angle of 180 degrees, a right angle of 90 degrees, and a triangle whose interior angles sum to 180 degrees. The right angle, marked with a small square, is the most common reference. Acute angles lie below 90 degrees, and obtuse angles fall between 90 and 180 degrees. For finer measurements, a degree is subdivided sexagesimally, meaning by 60s. 1 degree equals 60 arcminutes, and 1 arcminute equals 60 arcseconds. So 1 degree contains exactly 3,600 arcseconds. This three-tier system is still standard for navigation, astronomy, and surveying because the arcsecond is fine enough for almost any practical observation. The angular diameter of the full moon, for example, is about 31 arcminutes, roughly 1,860 arcseconds. Decimal degrees are also common, especially in computing and GPS. 45 degrees, 30 arcminutes, 0 arcseconds equals 45.5 degrees, because 30 arcminutes is exactly 1/2 of a degree. Figure 7. 3 views of the same 1 degree. On the left, a full circle where 1 degree is a tiny arc at the top. In the center, that arc zoomed in and subdivided into 60 arcminute arcs. On the right, 1 arcminute arc zoomed in further and subdivided into 60 arcsecond arcs. This base 60 hierarchy descends directly from Babylonian arithmetic and remains standard in navigation charts, astronomical coordinates, and geographic maps of latitude and longitude. Worked example: converting DMS to decimal degrees. Convert the angle 38 degrees, 53 arcminutes, 23 arcseconds to decimal degrees. Start by converting arcseconds to arcminutes. Divide the arcsecond count by 60. 23 arcseconds divided by 60 is approximately 0.3833 arcminutes. Add this fractional arcminute to the 53 whole arcminutes. 53 arcminutes plus 0.3833 arcminutes equals 53.3833 arcminutes. Convert the total arcminutes to degrees, divide by 60. 53.3833 arcminutes divided by 60 is approximately 0.8897 degrees. Add the fractional degree to the whole degree part. 38 degrees plus 0.8897 degrees gives approximately 38.8897 degrees. The angle is approximately 38.8897 degrees, close to the latitude of the White House in Washington, D.C. Try it. Convert 32.275 degrees to degrees, arcminutes, and arcseconds. Hint: multiply the decimal part by 60 to get arcminutes, then multiply the remaining decimal by 60 again to get arcseconds. Pause the video now and give it a try. Radians, the natural unit. Degrees are convenient and historical but they are arbitrary. There is nothing geometrically special about the number 360. The natural unit of angle measure is the radian, and it is the unit that makes every formula in advanced mathematics simpler. Take any circle of radius r. If you mark off an arc whose length along the rim is exactly r, the central angle subtended by that arc is defined to be 1 radian. The full circumference of a circle is 2 pi r, so a full revolution equals exactly 2 pi radians. Animation 1. A circle of radius r. A point starts at the rightmost position and moves counterclockwise, trailing a highlighted arc. The point stops the moment the arc length equals r, exactly 1 radius. The central angle swept from the start is labeled 1 radian. The arc continues, 2 radians, then 3, then pi at the halfway mark, and 2 pi as the point returns to its start after 1 full revolution. Figure 8. The definition of a radian, a circle of radius, r, with an arc of length equal to the radius, r, marked along the rim, and the central angle subtending that arc defined as 1 radian, approximately 57.3 degrees. 3 such arcs wrap a little more than halfway around the circle. Because pi is approximately 3.14, meaning 3.14 radii fit in a semicircle. Exactly 2 pi radians complete the full circle. Equation 1, s equals r theta, arc length s, the distance along the arc, equals radius r, times the central angle theta, measured in radians. Equation 1 contains no conversion factor, no pi, no division by 180. That is why radians are called the natural unit. The geometry and the algebra say the same thing with the same number. Equation 2. A equals 1/2 r squared theta. The area of a circular sector, the pi slice region between 2 radii, equals 1/2 times the radius squared times the central angle theta. Figure 9. A circular sector with both formulas labeled the curved rim carries the arc length s equals r theta, and the shaded interior carries the sector area a equals 1/2 r squared theta. The two formulas express the same angle theta at 2 scales, linearly along the rim for arc length and quadratically across the slice for sector area. A full revolution of 2 pi radians corresponds to 360 degrees, so pi radians equals 180 degrees. Numerically, 1 radian is approximately 57.3 degrees. Worked example. Arc length. A circular running track has radius 60 meters. You run an arc subtending a central angle of 2.5 radians. How far did you run? Identify the given values. Radius r equals 60 meters and central angle theta equals 2.5 radians. Apply equation 1. Arc length s equals radius r times angle theta. S equals 60 times 2.5, which equals 150 meters. You ran exactly 150 meters. Try it. A bicycle wheel has a radius 35 centimeters. The wheel turns through an angle of 4 radians. How far does the bicycle travel, assuming no slipping? Pause the video now and give it a try. Converting between degrees and radians. To convert from degrees to radians, multiply by pi over 180. To convert from radians to degrees, multiply by 180 over pi. Because the two factors are reciprocals, the same cancellation logic works in both directions. The unit you want to remove goes in the denominator and cancels. Figure 10. A balanced scale diagram, 180 degrees on the left pan and pi radians on the right pan, sit in perfect equilibrium. They represent the same angle. The two arrows show the direction of travel. multiply by pi over 180 to go from degrees to radians, or multiply by 180 over pi to go from radians to degrees. You should commit a small set of standard angle equivalences to memory. They appear in almost every trigonometry problem. Figure 11. Essential degree radian equivalences. 0 degrees equals 0, 30 degrees equals pi over 6, 45 degrees equals pi over 4, 60 degrees equals pi over 3, 90 degrees equals pi over 2, 180 degrees equals pi, 270 degrees equals 3 pi over 2, and 360 degrees equals 2 pi. Animation 2. A unit circle with a rotating radius pointer. As the pointer sweeps counterclockwise, the current angle is displayed in degrees above and in radians below, both values updating in real time. The pointer pauses at each standard angle, 30 degrees alongside pi over 6, 45 degrees alongside pi over 4, 60 degrees alongside pi over 3, 90 degrees alongside pi over 2, continuing through 180 degrees at pi, 270 degrees at 3 pi over 2, and 360 degrees at 2 pi, completing the full correspondence between the two systems. Worked example. Round trip. Degrees to radians and back. Convert 135 degrees to radians. Then convert 7 pi over 4 radians to degrees. For 135 degrees, multiply by the conversion factor pi over 180. 135 degrees times pi over 180 degrees equals 135 pi over 180. Simplify by dividing numerator and denominator by their common factor of 45. 135 pi over 180 simplifies to 3 pi over 4, approximately 2.356 radians. For 7 pi over 4 radians, multiply by the conversion factor 180 over pi. 7 pi over 4 times 180 over pi. The pi in the numerator and the pi in the denominator cancel, leaving a simple multiplication. 7 times 180 over 4 equals 1,260 over 4, which equals 315 degrees. So 135 degrees equals 3 pi over 4 radians, and 7 pi over 4 radians equals 315 degrees. Try it. Convert these angles to radians, writing each answer as a multiple of pi in lowest terms. 15 degrees, 72 degrees, 150 degrees, 240 degrees, and 330 degrees. Then convert these radian measures to degrees: pi over 12, 5 pi over 6, 11 pi over 6, and 5 pi over 3. Pause the video now and give it a try. That wraps up angles and how we measure them. Next up, Section 3, Right Triangle Trigonometry. If you found this helpful, like and subscribe and support the channel.